class. This is Econ 510 Managerial Economics class. Today is February 15th, Tuesday. Class will cover the second half of Chapter 5, the production theory.
Remember, we're talking about how economists describe the productivity of a firm. Eventually, we're going to use this information when we prescribe what a firm should do to maximize its profits. But for now, we're concerned with the task of representing a firm's technology. Last time we looked at the total product curve, which tells us what a firm can do in the short run when it can vary only one of its inputs. We also described the marginal product of a firm, that is the additional output that the firm can produce by hiring an extra worker, an extra unit of the variable input. What I'd like to do now that we've discovered that marginal product is simply the slope of the total product curve, is I would like to draw a picture that puts the marginal product curve in a graph by itself. Let's look now at this diagram, and we've got another one of these now famous two-story diagrams. Remember, the trick with a two-story diagram is the graphs are related and they have the same variable measured on the horizontal axis. So in this case, we are measuring labor input on the horizontal axis in both pictures. On the upstairs picture, we're measuring total product on the vertical axis, and we're using those same numbers that we've been using all along to represent a total product, and those numbers are next door. In the graph below, we're going to now represent marginal product, and I've shown you those numbers. I calculated them before. It's the change in output that results from a change in the variable input, and these are my marginal product numbers. They're also next door as well. What I'm going to see is that when the curve is convex, that is, when the curve is increasing at an increasing rate, the marginal product will be increasing. That is, the slope is getting steeper, the marginal product is going to be increasing. When the slope is decreasing, that is, when the curve is concave, when total product is increasing at a decreasing rate, then the marginal product will be decreasing. This marginal product curve will be downward sloping. Finally, when the total product curve finally maxes out and heads south, that is, when extra workers actually decrease the total product of the operation, then the marginal product will itself be negative. So I've put the points from this diagram, from this chart. I put the points down here in the marginal product curve, and now I'm ready to connect them and draw the marginal product. So for one worker, the marginal product is 2. For the second worker, it's 10. For the third worker, it's 20, and so forth. So here is 2. Here's 10. I made a mistake there. I don't know why I had that point for 10, because I'm using this for 10 and this for 20. So there's 20. You got to be careful about this. And that means when I go back to a marginal product of, oh, I know why, because that isn't a marginal product of 10, it's a marginal product of 8. Well, I got ahead of myself, so I can mark that point off. Here's what the curve looks like. 2, 8, 20, 10, 5, 3, 1, and -1. And hey, I'll save my mistake here by making it part of the picture. I'll use that as the letter P for my marginal product curve. Hey, there's a little lesson. Sometimes you can turn your mistakes into part of the art, and that's what I've done here. Now, the marginal product curve shows me the slope of the total product curve at every point. And by connecting the dots, you can see where the curve is convex, the X, the marginal product is increasing. Where the curve is concave, the marginal product is decreasing. And where the curve goes negative, the marginal product is below 0. So this curve represents the slope of this curve at every point. I want to throw in two little points of information here that you might find useful. Sometimes we write total product with an L in parentheses afterwards to indicate that total product, that is the total output that you can produce in the short run, given your technology and given your amount of fixed inputs, is a function of labor. So we write this as a function of labor. I could also write marginal product also as a function of labor. I could write MP of L, because the marginal product changes as I add additional workers to my factory. The next thing that I want to point out is that we're talking here about the number of workers who are working in the factory at a particular time. It's not like you're hiring one worker or then a second worker later in the week or a third worker even later. We're talking about 2 workers working together for a week or 3 workers working together for a week. See, the change in the marginal product is part of the technology. There are things that 2 workers can do to produce televisions that 1 worker can't do by herself. There are things that 3 workers could do that 2 workers can't do. Teamwork and specialization become possible as you add extra workers working together at the same time. So when we talk about the marginal product of technology, we're talking about how productivity changes as you add additional workers that are working at the same time, at once, together, over a given period of time, like a week. Finally, the last thing that I want to point out is I've been using the term convex and concave. I sometimes forget which is which, so I'll show you a little trick, a little memory trick. A memory trick, by the way, is called a mnemonic device. Some of my students were telling me the other day I'd used the expression mnemonic device, and they started telling me that they liked these demonic devices. They thought they were helpful. So here's a little demonic device to help you. Let's suppose you're standing here on the axis looking up at a curve, and if you're looking up and you see a cave, then we say that the curve is concave. But if you look up and you're looking for a cave and what you see doesn't look like a cave, if it's bowed downwards and you're looking for a cave, well then you would be frustrated or vexed. So this is convex. So here is where you're vexed, and here is where you actually see a cave. If the curve is concave, you look up and see a cave. If it isn't, then you're vexed. The curve is convex. So now we've got a picture of the marginal product curve, which is the slope of the total product curve. And what we'll add next is another measure of productivity that you may often hear about in the newspaper, that is output per worker. And that's called the average product of labor. So we'll describing the technology of the firm. And we've been focusing on the marginal product, the change in output that results from a change in the variable input when you hold everything else constant. Now we're going to look at another measure of productivity that becomes important later in the story. I'll give you a little hint about where we're going. Remember, our main concern is being able to recommend to a firm how much output to produce if it wants to maximize its profits. Well, the marginal product turns out to answer that particular question. The average product, on the other hand, this concept that we're about to introduce, tells the firm whether it's able to make a positive profit or not. That is, when a firm is doing the best it can, is it making a profit or a loss? So let's go ahead and introduce now the concept of average product of labor. That is, the total output divided by the total labor input. When you read the newspaper or hear discussions of labor productivity on the TV news, what people are talking about is average product of labor. How much output is the typical worker at a firm producing, the average worker? We define the average product of labor, again, as total output divided by the total number of workers employed. So if we look back at the tables we've been looking at, the particular television firm we've been considering, if we have one worker producing 2 televisions, then that means on average workers are producing 2 TVs apiece. 2 workers producing 10 televisions gives us an average product of labor of 5 TVs per worker. 3 workers producing 30 has an average product of labor of 10. 440, also an average product of 10. 545 gives us 9 TVs per worker, and so forth, on down the list. These numbers represent the average product of labor for different levels of employment inside the firm. That is, for different quantities of workers hired and different numbers of televisions produced. I'll move all these numbers now next door, and we will draw a picture of the average product of labor. We will draw a graph below the total product curve that represents the average product of labor. Now, I use the red for product. I kind of like red for output for some reason. And I used the red a minute ago to draw the marginal product curve. So in order to avoid confusion, I'm going to switch to green here to represent the average product of labor. So let's do that. The average product, again, is total output divided by the total number of workers. So up here we see that a total output of 2 televisions when we have 1 worker gives us an average product of labor of 2 TVs per worker. So I'll put this in at 2 TVs per worker. And here we've got 2 workers producing 10 TVs for an average product of labor of 5 TVs per worker. Then 3 and 30 gives me an average of 10 per worker, which is exactly what I get with 4 workers producing 40 TVs. And 5 workers producing 45 takes my average down to 9 TVs per worker. And then 8, and then 7, and then 6. So if I connect the dots here, I'm going to get an average product of labor curve that looks something like this. First it's increasing, then it levels off, and then it's decreasing. And I'll label this APL for the average product of labor, the output per worker, or the amount of output that the average worker produces. Output per worker, or labor productivity. Now, before, remember we said that the marginal product of labor was the slope of this curve at any given point? There's also a geometric way to calculate the average product of labor, but it doesn't make as much intuitive sense. It's actually the slope of a line from the origin up to the curve. The rise would be output, and the run would be labor, so output divided by labor would be the average. If you're interested, you can find the average product of labor by taking the slope of a line that goes from the origin up to any point on the curve. And as the points on the curve change, the slope of the line from the origin also changes, and that changes your average. That seems a little complex, and not a lot of, intuitive assistance do we get from that, so I'm going to leave that alone and go back to the curve that I drew from the numbers that I got from my table. That's just as easy a way of doing it. I want to notice a few things about this average product of labor curve. I want to notice a few things about it. First of all, again, it's kind of U-shaped. That is, first the curve slopes upward, and then it slopes downward. We reach a point of maximum labor productivity at some point. At some point, average product of labor reaches a maximum. That is, at some point, we are getting the maximum number of televisions per worker that we can get out of this factory, given its size, given the number of tools, given our technology, and so forth. That's thing one I want to notice. The average product of labor curve is like an upside down U. At first it increases and then it decreases. It's like a hill. The next thing I want to notice is I'm going to put the marginal product curve back in this picture. I'm going to draw it again, and it looks like this, you'll recall. Okay, so here's my marginal product of labor, and I've got it in red. Notice again that the marginal product curve first slopes upward when the curve is convex, and downward when the curve is concave, and then it goes below zero when the curve, the total product curve tips downwards. Well, notice something about the average product of labor. This is something kind of interesting, and that is when the marginal product of labor curve is above the average product curve is rising. And when the marginal product of labor curve is below the average product is falling. Now here's the intuition. If you're adding workers that are more productive than average, you're pulling up the average. Kind of like when you have a really good semester at school and you make a grade point, an overall grade point average that's higher than your cumulative GPA, you pull up your cumulative average by adding a semester that's above average. Over here, when we've got workers that are less productive than average, we're pulling the average down. Kind of like when you make a bad exam grade, an exam grade that's below your class average, you pull your class average down. You pull your own average for the course down by a below average score. When the marginal is above the average, it pulls the average up. When the marginal is below the average, it pulls the average down. That means that the marginal product curve is going to intersect the average product curve when the average product curve is at its maximum. That is, the marginal pulls it up and then pulls it down, and it intersects it, therefore, at the maximum of the average product. The intersection of the marginal product with the average product occurs at the point where the average product curve is at a maximum. Now that piece of information is going to become important later, knowing where the marginal product curve cuts into the average product curve. It cuts into it at the point where workers are producing, on average, the most televisions per worker that can be produced in this particular factory. This is the point when labor productivity is at its highest. There was a joke that we told at my school growing up about a rival school. Did you hear about the guy from our school who left to go to the rival school? He raised the IQ at both schools. Well, this is a joke about marginals and averages. That anybody who would leave our school must be someone whose IQ was below average, but he was still smarter than the average at the other school. So he raised the IQ at both places. Now, when you hear that joke and you laugh, what you're really laughing at is mathematics. You're laughing about this funny relationship between averages and marginals that makes it possible for you to take someone who's below average, move him over into another pool that has still a lower average, and raise the average in both pools. That's what this relationship between marginals and averages is all about. Well, that then completes our set of product curves. We've now done as much as we can to explain the technology of a firm in the short run. What we've done here is we've described the possibilities of a television factory that produces television sets using labor and some other fixed inputs. The firm can increase its output in the short run, but it can only do so by adding more labor. And we've described the productivity of labor by two concepts: the marginal productivity of labor, which depends on teamwork and specialization and on congestion, and the average productivity of labor, which is what we usually call labor productivity, or output per worker. We also describe the relationship between marginals and averages. When the marginal is above average, it pulls it up. When it's below average, it pulls it down. What's next? Next, we're going to take these notions of productivity and couple them with some information about input prices. And we're going to come up with a set of cost curves, a representation of the firm's cost of producing any given amount of output. Series of lectures that a lot of students consider very difficult. So we're going to take our time and try to do this extra clearly. We're going to be talking about the costs of production. Now, you'll recall we've just done a series of lectures on productivity, the firm's technology. Now we're going to talk about how you take the firm's technology, what they know how to do, and combine it with the cost of hiring inputs like labor and capital, and come up with the costs of producing output. In our case, the cost of producing television sets. This information is going to be very helpful to us when we move to the next phase, finding the profit-maximizing output choice for a firm. So here we are, technology, costs, and profit. We're in the middle of this stream of questions that's going to lead us to the answer, what is the best choice for a firm to make if it wants to maximize its profits? Students find this material difficult because it involves a lot of different tools used at once. We're going to be looking at charts and some simple mathematics. Then we're going to be looking at curves that represent the information in those charts. So I'm going to try to do this very carefully. I'll show you some charts, then show you the curves that go along with it. And at each stage, I'll try to remind you of the intuition behind all of it. Let me start with what I think is a very simple explanation of the relationship between costs and productivity. The first relationship we want to begin with as we start our discussion of the costs of production is the relationship between costs and productivity. In particular, costs and productivity are inversely related. That is, when productivity is increasing, the cost of production is falling. And when the productivity of your workers is falling, the cost of production is increasing. Let me see if I can make that very, very clear. Let's suppose we have a television factory. And in this television factory, we have a certain number of fixed inputs, like the size of the factory, the number of conveyor belts, the number of tools. And we also have variable input, that is, the number of workers that we hire to assemble television sets. Let's suppose we start with an assumption about productivity. Let's suppose we assume right now that one worker, given her know-how and the tools available to her, can assemble 1/4 of a television in a day. If one worker can assemble 1/4 of a television in a day, then how many workers will it take to make a whole television? The answer is, it will take 4 workers. 4 workers, each assembling 1/4 of a television, will produce for us a whole television. Now notice the point that I'm making. If one worker has an average product or an average output of 1/4 of a television, 1/4, then the reciprocal of that, 4 workers, is what it takes to produce a single television set. Notice, productivity and costs are reciprocal. If one worker can produce 1/4 of a television, then it takes 4 workers to produce 1 television. And you've got to pay those workers the wage, and that's what determines the cost of getting that television put together. 1/4 is the reciprocal of 4. If 1/4 is the productivity of the worker, then 4 is the number of workers it takes, which becomes your cost of producing the television. This idea, this simple explanation, is the basis of the relationship between costs and productivity. The more productive your workers are, the fewer workers you will need to produce your output. Now what I'm going to do is I'm going to go step by step through a description of the different notions of cost of production. We will look at the costs associated with hiring labor. We'll look at the costs associated with having a factory and tools ready for those workers to use. And finally, we'll look at the cost of producing another television set. What is the cost on average of producing a single TV, and what is the cost to produce 1 extra television set? The notion of average cost and marginal cost. Along the way, after I give you an example of each of these concepts, I'll be taking a break and then drawing the curve that goes with each concept, so that when you look at the picture, you won't just see a line on the page. Perhaps you'll also see a story that relates productivity to costs. That way, when we finally come to the point of using these curves to describe the firm's profit-maximizing choice, maybe you'll have some intuition that makes this more than just a technical exercise. I hope so. So we'll move now to the first concept of cost, and that is the cost of hiring the labor to produce your output, the variable cost of production. Series of lectures where we introduce the concepts that we use to describe the costs of production for a firm. The first concept that we're going to introduce is the concept of variable cost. The variable cost of production is the cost of hiring the variable input needed to produce a given amount of output. That is, in our case, the amount of money the firm has to spend to hire the labor that it needs to make a given quantity of television sets. In order to find the variable costs for a particular firm, you're going to need two pieces of information. The first piece of information we've already discussed. This is the amount of labor that the firm needs to produce a given quantity of output. And this is an idea about productivity. Remember the total product of the firm? It told us how much labor we needed to produce a given quantity of televisions. So the first piece of information you need is a piece of technological information. How much labor do we need to hire to produce a given quantity of television sets? The second piece of information that you need is a piece of economic information. That is, how much do you have to pay to get a unit of labor? In other words, what is the wage rate that you must pay your workers in order to get them to work for you, assembling television sets? Once you know how many workers you need and what you have to pay each one of them, then you've got the variable cost, or the labor cost of producing a given quantity of television sets. Let's suppose, for the sake of our example, that the wage for a television set assembly worker is $1,000 per week. That means every time a firm hires another television assembly worker, they've got to pay that laborer $1,000 per week. Let's now use that information to find the variable cost of producing certain quantities of television sets. Go back to the chart that we began with. This chart describes the production possibilities of the firm. That is, how many television sets a certain number of workers can assemble in a week. What we'll do now is take the number of workers in each case and multiply by the wage that must be paid those workers to get the total amount of money the firm has to spend on labor to produce output. For instance, if you hire one worker, you've got to pay that worker $1,000 a week for a total of $1,000. That's the variable cost of producing 2 television sets. Because after all, one worker can produce 2 television sets. That means $1,000 is the labor bill for turning out those 2 television sets. If you hire 2 workers, you can produce 10 television sets. And since each of those workers will cost you $1,000 per week, the variable cost of producing 10 television sets is $2,000. Keep going. To produce 30 television sets, you need to hire 3 workers. That's $3,000 a week. To produce 40 television sets, you have to hire 4 workers. That's $4,000 per week, and so forth. All of the numbers in this column are calculated by multiplying the number of workers you need by the wage of $1,000 to get the variable cost of producing a given quantity of television sets. Now, you might ask yourself, well, what's it going to cost us to produce 35 television sets a week? Well, we can't say for sure because we don't have enough detailed information here to answer that question, but we know that it takes between 3 and 4 full-time workers per week to produce 35 television sets. So the number lies somewhere in between those two, which means the variable cost will be somewhere between $3,000 and $4,000. Again, you can imagine a fractional number of workers to give you a particular number of television sets and then multiply that by $1,000 per week to get the variable cost. Once again, the variable cost is simply total spending on the variable input needed to produce a given volume of output. What we'll do next is draw a picture of this concept. Draw the first of our cost curves. We're going to be drawing a lot of these cost curves, so I'm going to take special care with this one to kind of show you how they work. Next door, you can see the numbers that we used last time whenever we derived a relationship between cost and output. This is our variable cost series. It tells us how much money we have to spend on labor in order to produce a given number of television sets. What I'm going to do now is draw a picture of that relationship, and this relationship will be called the variable cost curve. The variable cost curve shows you how much money you have to spend on labor in order to produce a given number of television sets. Let's look at the way this graph will be set up. On the horizontal axis, I'm going to measure the number of television sets that we're producing in our factory. On the vertical axis, I'm going to be measuring dollars, the amount of money we're spending to hire the labor to produce those television sets. So use the numbers from over there, and we'll put them in the graph and come up with a variable cost curve. Ask the question, how much does it cost us to produce 2 television sets? How much do we have to spend on labor? And the answer, as you can see next door, is $1,000. So we'll put a dot here to represent 2 television sets and $1,000 worth of spending on labor. Next, how much does it cost us to produce 10 television sets? Well, you can see it cost us $2,000, so put a dot there at 10 televisions and $2,000. To produce 30 televisions, we're up to $3,000 worth of spending on labor. To produce 40 televisions, we're up to $4,000 worth of spending on labor. And we can produce 45 televisions by spending $5,000 on labor, 48 televisions by producing with 6 workers, that cost us $6,000 a week, 49 televisions with 7 workers for a total labor cost of $7,000, and finally we've got this odd point up here, this odd point that says if we hire 8 workers, which costs us $8,000 a week, we can produce only 48 televisions. Remember before, I told you that this point is inefficient because you can produce the same number of televisions with less money spent on labor. That's why I'm putting an X on this point. We're not going to consider this point on the variable cost curve because no firm in its right mind would ever operate at that point. That is a point of inefficiency. So we're going to leave that point off the curve. Now, are these the only number of television sets we might be interested in producing? No. We might be interested in producing any number that lies along this axis. That means that we could have labor expenses that vary probably continuously from 0 all the way up to and beyond along the curve. So all the points in between are possible. And we represent that continuity by connecting the points and forming a curve. So here's what we get. We go from 0 up to $1,000, up to $2,000, then on up to here, and so forth. And eventually, my variable cost curve simply becomes vertical. And the variable cost curve, when it becomes vertical, represents the fact that you can spend all the money that you want to on labor, but you can't produce any more television sets. Once the total product of our factory has reached a maximum, the firm can spend more money if it wants to on labor, but it can't produce any more televisions. And as we looked at the numbers before, we saw that the maximum total product was 49 television sets. That's the most we can ever produce. So at that point, our variable cost curve will go vertical. You can hire more labor, but you can't get any more output. One final thing, let me label this curve variable cost, VC. This curve represents the amount of money that you spend on labor to produce a given quantity of output. Now that we've got the variable cost curve, I want to show you a little trick using another set of graphs that represents the relationship between productivity and cost. Remember, I told you that relationship is inverse. Productivity and cost vary inversely. I want to show you how that looks comparing our product graph with our cost graph. The relationship between cost and productivity one more time. This time, we're going to look at how average variable cost is related to the average product of labor. Now, stop for just a minute and make sure you're clear on what these concepts are. The average product of labor is the amount of output that your factory produces divided by the total number of workers you're hiring. That is, average product of labor is the output per worker. Average variable cost is your total spending on labor divided by the output that you produce. That is, it is your labor cost per unit of output. Now, how are these two concepts related? I'm going to do a little bit of math, like I did before when I discussed the marginal product and the marginal cost, and I'm going to show you mathematically precisely what I mean by the relationship between average variable cost and average product. Then I'll give an intuitive explanation, and then I'll show you some graphs that summarize this relationship. First, let's look at some math. The average variable cost is equal to what? It's equal to the variable cost, that is the total amount of money that your firm spends on labor, divided by the total amount of output that you produce, the total product of labor. So here is spending on labor, here are the number of televisions you produce. Well, the variable cost, as we've said before, is equal to the wage multiplied by the number of workers you hire, and we can divide that by the total product of labor. Well, if that's the case, then I can divide the numerator and the denominator of this fraction. I can divide both parts of the fraction by the number of workers that we hire, and we get this. W, that is the wage, divided by the total product of labor over the number of workers. Now, what is this term? What is this term right here in the denominator of my fraction? It's the average product of labor, output per worker. So the average variable cost is equal to the wage divided by the average product of labor, AP. What have I just proved? I've just used a few steps of math and logic to prove that the average variable cost, that is the labor cost per television you produce, is equal to the wage divided by the average product, that is the output per worker at your firm. Let's see if I can make this a little bit more intuitively clear with an example. And again, I'll use the example we had before. Let's suppose that one worker can, on average, produce 1/4 of a television set. If one worker can, on average, produce 1/4 of a television set, then it's going to take 4 workers, on average, to produce 1 whole television set. If the average product of labor is 1/4 of a television per worker, then it takes 4 workers to produce a television set. That means you've got to hire 4 workers at $1,000 each to produce a television set, and that's going to be the labor cost per television set, $4,000. If, however, one worker can produce half of a television set, if one worker can produce half of a television set, then it's only going to take 2 workers to produce a whole television set, and that means your average labor cost is only going to be $2,000 per television set. The more workers it takes to produce a television set, the higher your cost. And the lower the labor productivity, that is, the less that a given worker can produce, the more workers you have to hire to produce a whole television set. This is the relationship between productivity and costs. When average product is higher, then it takes fewer workers to produce a television set, and the average labor cost is therefore lower. Let's look now then at the relationship between the average variable cost curve and the average product curve. And here I have it drawn. When the average product of labor is increasing, that is, when it takes fewer workers on average to produce a television set, when one worker can produce more of a television himself or herself, then the average variable cost is falling. As workers become more productive, it takes fewer workers to produce a television, and the labor cost per television is falling. Finally, the average product reaches its maximum. And after that point, if you hire extra workers to produce more television sets, the average product of labor is falling. That is, the typical worker now produces less and less and less and less. That means you've got to hire more and more and more and more workers in order to produce a television set, and the cost per television is going up. The labor cost per television increases as the average product of labor falls. Now, you can look at these two diagrams again and see that they are very, very closely related. When average product is increasing, average variable cost is falling. When average product is at its maximum, the labor cost per unit is at its minimum. When average product begins to fall again, average variable cost begins to rise. The curves are mirror images of each other. This looks a lot like the same kind of picture we saw a few minutes ago when we compared the relationship between the marginal product curve and the marginal cost curve. Now, what we're going to do is put all of this together and look at the relationship between marginal and average product on one hand and marginal and average variable cost on the other hand. Let's focus on the put together the things that we've done in the last few lectures. In particular, we're going to draw one graph that has in it the marginal cost curve and the average variable cost curve. And when we draw the two curves together in one graph, we'll see a relationship between marginal cost and average variable cost. The relationship that we discover will be the same relationship that we discovered between the marginal product curve and the average product curve. Marginals and averages always have the same relationship. That is, when the marginal is above average, when you're adding things at the margin that are above average, you pull the average up. When you're adding things at the margin that are below average, you pull the average down. We'll see that same relationship now as we draw the marginal cost and average variable cost together in one graph. Let's start with a picture of the marginal cost curve. This is a review. Remember, the marginal cost is just the slope of the variable cost curve at any point. So when you're going to draw the marginal cost curve, what's the first point that you should look for on the variable cost curve? The first point that you look for is the point of inflection. That's the point where the slope stops decreasing and starts increasing. And that will be the point where the marginal cost curve reaches a minimum. So I'll go ahead and put that curve here. Now, if I want to draw a marginal cost curve, I'll look over here and see the region where the slope of the variable cost curve is decreasing, and that will give me a decreasing marginal cost. So over in this region, marginal cost is decreasing. Over in this region, marginal cost is increasing, and it's headed towards infinity as the variable cost curve goes vertical. So if I'm careful here and find where that variable cost curve is going vertical, I can draw a marginal cost curve that represents the slope of the variable cost curve. And now I can label this curve marginal cost, just like before. The marginal cost curve shows me the slope of the variable cost curve at every point. Now, how do I draw in the average variable cost curve? How do I draw it in? Well, here's what we know about average variable cost. We know that average variable cost is going to hit a minimum point where marginal cost curve cuts through it. Why? Because if the marginal cost is above average variable cost, it's going to be pulling it up. And if marginal cost is below average variable cost, it's going to be pulling it down. So, in that case, what we get is a curve that looks something like this. Now, how did I draw this curve the way I did? I drew it because I know that any time marginal cost is above average variable cost, it's pulling the average up. The AVC will be increasing. Anytime marginal cost is below average variable cost, it's pulling the average down. The average will be decreasing. That means that if average variable cost is its usual U shape, that the bottom of the U, the minimum point, has to occur where it touches the marginal cost curve, where it cuts through it. Now, the only thing that I haven't explained in my geometry here is how did I choose this particular point for the intersection? How did I choose that point? And the answer is not easy. The answer is going to involve knowing something else about geometry. In fact, the way I got this was I used a ray from the origin upstairs to touch the variable cost curve. A ray from the origin has a slope that's equal to variable cost divided by output. Notice I didn't label my axes here. Now, why did you let me get by with that? If you don't label your axes, you're not measuring anything. Back to my ray from the origin. My ray from the origin here goes up and touches the variable cost curve at this point. Now, what does the ray from the origin tell you? Well, the slope of the ray from the origin is rise over run. And the rise is the variable cost, and the run is the output. Well, what is variable cost divided by output? That's right. It's the average variable cost. So, at this point, the ray from the origin is at a minimum. That is, if we take this ray from the origin to other points on the variable cost curve, it's going to have a higher slope. Here, it's going to be at a minimum. If I go beyond that, the slope goes back up. That's a little geometric tidbit for you that lets you know why I picked that particular point. Your teacher is probably not going to require that you understand that. But I always like to know, well, why did he pick that point instead of some other point? The point that you pick for the minimum average variable cost is the point where a ray from the origin would just touch the variable cost curve. That's the point where the average is lowest. Well, the point that you do need to understand, that your teacher will want you to understand, and that really is important intuitively, is that anytime the marginal is below the average, it's pulling it down. And anytime the marginal is above the average, it's pulling it up. One more thing I'd like to say, and that is, if I flip this diagram over and look at this picture, does this look like anything you've seen before? Well, you may have trouble seeing it because the green is kind of pale, but I'm going to go over it again in red and hope that it looks familiar to you. This is the marginal cost curve turned upside down. It's mirror image. What's that going to be? What's the mirror image of the marginal cost curve? The marginal cost is reciprocally related to the marginal product. So I can label this MP. And here's the average variable cost. I'll go over it in red. The average variable cost is, of course, the mirror image of the average product of labor. So if I flip those graphs upside down, I've got a picture that should look very familiar to you. This is the picture we drew a few lectures ago, where we put labor on the horizontal axis and output on the vertical axis, and we showed how marginal product and average product were related to each other. Marginal product and average product are the reciprocals of marginal cost and average variable cost. And again, the intuition is the more workers it takes to make a television, the more it's going to cost. And the lower a worker's productivity is, that is, the less output a single worker can produce, the more workers it takes to produce an extra unit of output. That's the marginal idea. Or on average, if one worker on average produces 1/4 of a television, then on average it takes 4 workers to produce a whole television. That's the average concept. Productivity and cost are inversely related. You've seen it mathematically, you've heard a story about it, and you've seen how these graphs resemble each other. They're mirror images of each other. Cost and productivity are reciprocally related. That's the most important relationship in this series of lectures. However, there's one other relationship that's important also, and that is the relationship between marginals and averages. When the marginal is above average, it pulls it up. When the marginal is below average, it pulls it down. About a firm's decision in the short run. The short run is a period of time when some of the firm's inputs are fixed and some are variable. We're imagining that we're in a television factory, a factory that turns out television sets by using labor and other inputs. And those other inputs include a factory, the size of the factory space, a conveyor belt, tools, anything else that they might use. But all of these other inputs are fixed in the short run. Now, if you want to calculate the cost of production, you have to not only consider the variable costs, which we've been studying, the cost of labor, but you also have to include the fixed costs. Now, the interesting thing about fixed costs is they're very easy to calculate because they don't vary with anything. That's the definition of fixed costs. Fixed costs are costs of fixed inputs. They are fixed. They do not change. No matter how many television sets you produce, no matter how many workers you hire, fixed costs are fixed. So you can look at a table like this one right here, and no matter how many television sets we produce, the fixed costs are going to be a constant $10,000. That's going to be our assumption. $10,000 is the cost of all of the inputs that we have to pay for that we cannot vary in the short run, including our tools, our conveyor belts, our factory space, etc. So whether we produce 2 television sets, 10, 30, 45, 48, 49, whatever, our fixed costs are all going to be 10,000. So fixed costs are constant. They are fixed. However, the more television sets we produce, the more we can spread our fixed costs out over the individual television sets. If you only make 2 television sets, then the fixed cost per television is going to be $500 or $5,000. 10,000 divided by 2 is $5,000. You can only spread your overhead, your fixed costs, over 2 sets, and that means $5,000 per set, and that's very expensive. But the more sets you produce, the more thinly you can spread your fixed costs out. If you produce 10,000 television sets, your fixed cost per set will go down to only $1. So the more you produce, the more your fixed cost per unit shrinks. This fixed cost per unit has a special name. Can you guess what it is? It's the average fixed cost, of course, the fixed cost per unit of output produced. In order to calculate the average fixed cost, what you want to do is take the fixed cost, divide by the number of television sets produced, and that gives you the average fixed cost. 10,000 divided by 40 televisions is $250 per television set. 10,000 divided by 49 television sets is $204 per television set. Notice that as long as you're producing more television sets, your average fixed cost is getting smaller and smaller and smaller. If we ever went into an inefficient production where we added more workers and the number of television sets produced actually decreased, well, in that case, our average fixed cost would be rising again. But as long as you produce more sets, average fixed cost is shrinking. Let's draw a picture of average fixed cost, and I'll move all these numbers over there so that you can use them for reference. If you want to draw a picture of average fixed cost, what you'll find is that average fixed cost is what we call in geometry a rectangular hyperbola. Now, that's a mouthful, and it refers to a curve that approaches both axes asymptotically. If you're producing very, very few television sets, then your fixed costs per unit are going to be very high. But the more television sets you produce, the more the average fixed cost is going to get closer and closer to zero. So I can label this curve average fixed cost. It's very high when you're not producing many television sets. It then shrinks, and the more television sets you produce, the smaller it gets. This is spreading your overhead out over more and more television sets. Now, let's take this average fixed cost, and let's put it together with another diagram, another graph that we're used to drawing, another curve, and that is the average variable cost curve. So let's draw the average variable cost curve in here. And remember, it looks like this, AVC. So now we've got two curves together. The average fixed cost, which is the cost of your tools and your other fixed inputs, and the average variable cost, which is the cost per unit of the labor that you need to hire. Well, together, your variable costs and your fixed costs make your total cost of production. So if you have average variable cost and you add it to your average fixed cost, you're going to get your average total cost. The total amount that you have to spend on labor and everything else per television that you produce. Now, how do you calculate this average total cost curve? Where do you get it? Well, you can get it a couple of different ways, but since we're in a graph, let me show you how it looks graphically. If you take the average fixed cost of producing a given number of television sets, right here, and you add it, the average variable cost of producing a given number of television sets, I've got to be careful here because I've got two curves, so I've got to make sure which one I'm looking at. And you add that to the average fixed cost. If you add these two together, then if I take this amount and put it on top of this and add them together, I get the average total cost. The average total cost is just average fixed cost added to average variable cost. And if I add the two together, then I'm going to get a curve. So by vertical addition, I'm going to get a curve that looks something like, let me find a couple of other points on it. Here's one. Add those two together. And eventually I'm going to get a curve that looks like this. And there's my average total cost curve. The average total cost curve is the sum of the average variable cost and the average fixed cost. This is how much it costs our factory to produce television sets per unit, including the cost of labor and the cost of other inputs. Talking about the total cost of producing a given quantity of television sets. Eventually, you're going to want to figure out whether your operation is profitable or not. And in order to figure that out, you're going to need to compare the money that you earn from selling a television set with the cost of producing the television set. In order to find the cost of producing an individual television set, you're going to need a new cost concept, and that is the concept of average total cost. Average total cost is the total cost of producing television sets divided by the number produced. It tells you the labor cost as well as the cost of all of the other materials that go into making an individual television set. Average total cost. Average total cost is defined as total cost of production divided by the number of units of output produced. Let's look at some numbers. We've calculated the total cost of producing any given number of television sets. For example, if you produce 2 television sets, you're going to have a total cost of $11,000, $1,000 for labor and $10,000 for fixed costs. If you divide $11,000 by 2 television sets, you find out that the total cost on average is $5,500. That is, it costs $5,500 when you're producing 2 television sets to produce 1 television set. $5,500 is the average total cost. Well, you can follow this logic on down the page and calculate the average total cost when you're producing 10, 30, 40, 45, and so forth. So the first method of calculating average total cost is to take the total cost of production and divide by the number of television sets produced. There's also another way of calculating average total cost, and this one is going to turn out to be useful to us in a minute when we derive the average total cost curve graphically. Remember, total cost can be broken into two components, fixed cost and variable cost. If you think about it, fixed cost and variable cost can both be divided by the total number of units of output, just like we can divide the total cost by the total number of units of output. Total cost divided by the total output is equal to average total cost. But you know that the total cost is just equal to the variable cost, that is the cost of the labor that goes into production, plus the fixed costs, the cost of the fixed inputs. Well, if we divide both sides of this equation by the total number of television sets produced, you can see another way, a way that might be easier sometimes, of calculating average total cost. Divide both sides by the total number of televisions produced, that is the total product, and you get this. Total cost divided by total product is equal to variable cost divided by total product plus fixed cost divided by total product. But you know what these two terms are. Each of these terms has its own definition. Variable cost divided by total product is what? That's right, it's the average variable cost. And fixed cost divided by total product is what? It's the average fixed cost. So the total cost on average, the average total cost, is equal to the average variable cost plus the average fixed costs. Now you can see that if we look at our numbers. Average variable cost is right here. Average fixed cost is right here. And here's our schedule that tells us how many televisions we're producing. If we put all of these together, and I don't want the marginal cost curve at all, that's the curve I don't want. The curve that I want is average total cost, which I've put over here. Look, in each case, the average total cost of producing a given number of television sets is equal to the average variable cost plus the average fixed cost. 200 plus 1,000 is 1,200. 111 plus 222 is equal to 333. By way of summary, let me say this. There are two ways of calculating the average total cost. One is taking the total cost and dividing by total output. The other way is to add together the average variable cost and the average fixed costs. That gives you average total costs. Now, we'll represent all of these curves together in a single graph. We'll put the average variable cost curve together with the average fixed cost curve and derive the average total cost curve. And the method that we'll use is the method of vertical summation, the same method we used a little while ago when we first drew the total cost curve. Another question that students ask is, when do you move along the cost curves and when do the cost curves shift? Let's see if I can answer that one. Over here, we have the long run and the short run cost curves, and I've reproduced them over on the board so that we can talk about them. First, anything that changes the price of the firm's product is going to cause a movement along the cost curves. Remember, you can never shift a curve by changing what's on one of its axes. You can only shift a curve by changing something that isn't in the picture. You can only shift a curve by changing something that you're holding constant when you draw the picture. So if the price of the firm's product changes, you will move along the curve. In the short run, the firm will move along the short run marginal cost curve. And in the long run, the firm will move along the long run marginal cost curve as the firm expands its output. However, if you change one of the things that's held constant when you draw this picture, then you'll shift the whole set of curves. For instance, let's suppose that the price of the firm's inputs increase. Let's suppose that the price of labor and capital increases. In that case, what will happen to the cost curves is this. The whole set of cost curves will shift upwards, representing an increase in the cost of producing any given quantity of output. If the price of the inputs falls, then the cost curves will all shift downwards, representing a reduction in the cost of producing any quantity of output. The next thing that could shift the cost curves would be a change in technology. If the firm's technology improves, that is, if it can make more output with a given amount of input than before, then the cost curves will shift downwards, because now the firm can produce its target level of output with less input, and therefore at lower cost. So the thing that will shift the cost curves will be a change in the price of the firm's inputs or a change in the firm's technology. One more thing to point out. I told you a moment ago that when the firm moves into the long run and changes its quantity of capital, there is a shift in the short-run supply curve. That shift occurs not because the short-run marginal cost curve actually shifts, but because the firm moves from one short-run marginal cost curve to another short-run marginal cost curve. Remember, anytime you change the amount of the fixed input, you have to change the short-run marginal cost. The short-run marginal cost is based on labor productivity, which depends on the amount of tools or capital that the workers have to work with. Anytime you pick a point on our blue long-run average cost curve, anytime you pick a point, you can hold capital constant and draw a new green curve that's tangent at that point. If firms acquire more capital in the long run, they're going to be moving from this set of short-run cost curves to another set of short-run cost curves at a different point on the long-run average cost curve. So it's not that the green curve actually shifts for a single firm, it's that you move from one set of short-run cost curves to another set of short-run cost curves. In the last lectures, we discussed the first problem that the firm faces in the long run. That's the problem of choosing the cost-minimizing technique, the way of combining capital and labor so as to minimize the cost of producing a given quantity of output. In this lecture, we're going to consider the second problem that the firm faces in the long run, and that is the choice of the optimal scale, the right size of operation for maximizing your profits. In the short run, the firm can't help but change its scale and change its technique at the same time. If the firm wants to produce more output in the short run, they've got a fixed amount of capital, and they can only increase output by adding more labor. That means that in order to increase the size of their operation, or their output of television sets, they've got to add more workers, which increases the intensity of labor. That is, we're using more labor per unit of capital. So they're also choosing scale, the size of their operation, at the same time as they're choosing the technique of production. 3 workers and 1 tool may be the only option that's available to the firm for increasing their output in the short run. The firm is simultaneously choosing the technique of production and the size of their operation. In the long run, the firm gets to choose these 2 things separately, which is one of the reasons why long-run costs of production are always lower than the short-run costs. The firm has more flexibility. If the firm wants to increase the size of its operation, it doesn't necessarily have to use more labor per unit of capital. It can also increase the amount of capital that each worker has, thereby keeping the labor-capital ratio constant even as its firm grows bigger. That is, it keeps the cost-minimizing technique that it prefers while allowing the scale of operation to grow larger. The definition of the scale of operation is as follows. Scale is said to increase if the firm has a proportional increase in all of its inputs. So if we start with one worker and 1 unit of capital, the scale of the firm is said to increase if we add a second worker with a tool of his own and a third worker with a tool of her own. To have an increase in the scale, it is required that all inputs increase by a particular proportion, that they all increase by the same proportion. If we just increase labor and hold capital constant, that is not a change in scale. If we just increase capital and hold labor constant, that is not a change in scale. To change the scale of operation, you must have a proportional increase in all of the factors of production. Now, here's the question that we want to answer. How does the firm's productivity change as we change the scale of operation? In order to answer that question, we're going to need to define a concept very specifically, and that's the concept of economy of scale. What happens to the firm's productivity when the scale of its operation changes? Suppose we go from 1 worker with 1 unit of capital to 2 workers and 2 units of capital. What happens to output? Well, you can imagine that one of 3 things would happen. The first is probably the most reasonable assumption, and that is that if both of our inputs double, our output would double as well. This is the case when the firm is said to have constant returns to scale. Constant returns to scale is defined as a technology where increasing all inputs by a given proportion increases output by the same proportion. The reason this seems like a reasonable assumption is the possibility of replication. If we've got a guy over here making television sets by using a particular tool, and he can make 10 television sets a day, if we have another worker who has the same toolkit, we would imagine that that worker could also make 10 television sets a day. Replicating this operation would allow us to double the amount of output we get in a single day from our factory. If we had a third worker also with a tool, we should be able to replicate the operation again. Tripling inputs, we would expect to be able to triple output. That is the idea of constant returns to scale. And it seems like a reasonable assumption because of the possibility of replication, having someone else do what another worker with his tools is already doing successfully. Now, there are 2 other possibilities. The first is the possibility that things are actually better than constant returns to scale, that adding a worker with a tool, adding a second worker with a second tool allows us to more than double our output. That is, if we have 1 worker with 1 tool producing 10 television sets, 2 workers with 2 tools might actually be able to produce 30 television sets in a day. That would be the case if somehow there's some kind of teamwork and specialization between these workers. If working together, they can operate in a way that's more productive than if both of them work separately. Having the workers work together and cooperate, using their labor and tools together, may actually allow them to be more productive than 2 workers simply replicating what each other are doing. This is the case with increasing returns to scale. The final possibility is the possibility of decreasing returns to scale. It may be that by doubling all of our inputs, we actually increase output by a smaller proportion, maybe only 10% or 20%. Now, you might ask yourself, why would we ever have decreasing returns to scale? What could ever lead to a situation where 2 workers with 2 tools would do less productive work than they could do if they were working separately? And it has to do with the problem of a growing organization. As an organization gets larger and larger, you have more and more activity under a single manager. And that manager is responsible for making decisions about how this process is organized, how the workers are paid, how they are scheduled, how their activities are coordinated. When you've got a manager who's over this whole operation, it may be that the individual workers say to themselves, hey, rather than trying to make my money by working harder producing television sets, I'll go and lobby the manager for a raise. I'll go and ask for favors. I'll ask for a better schedule. I'll try to use my influence to improve my position in this organization. This is a form of rent-seeking, and it goes under the name of influence activities. Influence activities are efforts on the part of the workers to influence the organization to their advantage. And the cost of these influence activities is this. When workers believe that they can get more benefits by lobbying the boss, they'll spend less time actually producing televisions for the firm. Because of that, as the organization grows larger and the manager has more and more power, it is a greater and greater temptation for the individual workers to engage in influence activities rather than to produce television sets. And the cost of production then goes up as the firm has to employ monitors to make sure that people stay on the job and don't spend their time taking too many breaks, going and lobbying the boss, and such things like that. This is the idea behind decreasing returns to scale. As the firm gets very large, the problem becomes managing workers and preventing them from engaging in influence activities. So, this is the idea of scale economies. The firm wants to consider, what is the potential for teamwork and specialization? What is our scope for enjoying increasing returns to scale? Because as long as we're enjoying increasing returns to scale, it will probably pay for us to expand our operation. Also, we want to know, are we likely to have constant returns to scale? Because anytime a firm has constant returns to scale, replication is a possibility. And finally, there's the problem of decreasing returns to scale. If the firm grows too large, its workers are tempted to engage in influence activities, thus raising the cost of production. In the next lecture, we'll see how economies of scale translate into the costs of the firm in the long run.